Hi, happy to see you in the next part of the lecture. So here we'll talk about how differentiability is related to continuity. So suppose we have a function that's differentiable at x equal to x naught. We want to ask whether it follows that f is continuous at x equal to x naught. So when we say that f is differentiable, that means f prime of x naught exists. So with this assumption, to check for continuity at x equal to x naught, we have to determine then whether or not the limit of f of x as x approaches x naught is equal to f of x naught. Now, since we know that the derivative exists at x naught, then the function must be defined at x naught, right? That means f of x naught exists. So with that, we can rewrite the limit of f of x as x approaches x naught as limit of f of x minus f of x naught plus f of x naught. We can do this because the sum of the last two terms is equal to 0. Then we can apply the limit theorem for the sum of two terms, right? And then for the first term, we can multiply this by the unit x minus x naught all over x minus x naught, right? So this is just equal to the multiplicative identity, so it doesn't change in any way the limit in the first term. Moreover, for the second term, so we just have a limit of the constant, so this gives us f of x naught. For the first term, we can apply the limit theorem for products, right? And notice that the first factor in the first term is actually what? The derivative at x naught, right? The second factor, we can evaluate the limit of x minus x naught as x approaches x naught. So this will give us 0. So that leaves us with f of x naught. This proves then the theorem that if a function is differentiable at x equal to x naught, then it must follow that the function is continuous at x equal to x naught. Okay, now what if we have a discontinuous function? Can we say something about its differentiability? Well, if you recall, right, one of the conditions for which a function would not be differentiable is when the function is discontinuous, right? So from here, we know that when it is discontinuous, it is not differentiable. Now, you can also observe that our theorem says that if it is differentiable, so let's call that statement D, then it will follow that the function is continuous. So let's call that statement C. So D implies C. If you remember, the implication is equivalent to its contrapositive. In other words, if the implication is true, because the theorem is true that D implies C, it is also equivalently true that the negation of C implies the negation of D. That is called its contrapositive. Thus, because the theorem is true, therefore it is always true that if a function is discontinuous at x equal to x naught, then it is not differentiable at x equal to x naught. Now, what if we have a function that is continuous at x equal to x naught? Does it follow then that the function is also differentiable at that point? Well, if you remember the absolute value function, it was continuous at x equal to 0, but we were able to show that it is not differentiable at x equal to 0. So here we have a counterexample to that statement. Therefore, if the function is continuous, it does not necessarily mean that it is differentiable. So C does not imply D. Okay, lastly, what if the function is not differentiable at a point, say x equal to x naught? Can we say that it is also not continuous at x equal to x naught? Well, if you consider again the absolute value function, right, we have shown that that was not differentiable at x equal to 0, yet it was continuous at x equal to 0. Thus, the negation of D does not necessarily imply the negation of C. Okay, now let's take a look at one-sided differentiability and continuity. Let's consider a function with this graph right here. So we have the jump discontinuity at x equal to x naught. Notice that the function is continuous at x equal to x naught from the left, but it is discontinuous at x equal to x naught from the right. Moreover, if we consider second lines for which x approaches x naught from the left, we see that the left derivative at x naught exists. Also, if we take any point from the left, the derivatives exist at each of these points. In fact, if you look closely, the tangent lines at each of these blue points approaches the same line to which the second lines from the left approaches to. In essence, the limit of f prime of x as x approaches x naught from the left is the same as the left derivative at x naught. And this is actually true, right? We have the theorem that if a function is continuous at x equal to x naught from the left, and we know that the limit of f prime as x approaches x naught from the left exists, then the left derivative at x naught is just the limit of the derivatives as x approaches x naught from the left. Moreover, if we know that the function is continuous from the right and the limit of the functions as x approaches x naught from the right exists, then we can also say that the right-hand derivative at x naught is equal to the limit of the derivatives as x approaches x naught from the right. Now remember that the assumption here is it has to be continuous from the left if we're taking the left-hand derivative, or the assumption is that it has to be continuous from the right if we're taking the right-hand derivative. So going back to our example here, the function is discontinuous at x equal to x naught from the right. Now, if you take any point on the right of x naught, we see that the derivatives exist at each of these points. In fact, the tangent lines at each of these points approaches this lighter blue line right here. However, if we look at the second lines from the right, this does not go, unfortunately, to that blue line. In fact, what we end up here is a vertical line, so therefore the right derivative at x naught does not exist. Since they do not go to the same line, then the limit of the derivatives as x approaches x naught from the right is not equal to the right derivative at x naught. So remember, if you want to use this theorem to evaluate the left derivative or the right derivative, you have to first check the continuity from the right or the continuity from the left. Okay, let's try that with this example. Let's consider a function that's defined piecewise as x squared when x is less than -1 and -1 minus 2x when x is greater than or equal to -1. We want to determine if this function is differentiable at x equal to -1. So first, what did we say? Check for continuity. Okay, so first we evaluate the function value at x equal to -1. So we need to take the second condition, that is where x is equal to -1. So -1 minus 2x, if x is equal to -1, that gives us 1. Next, we evaluate the limit from the left. So that would be the first condition, right, where x is less than -1. So this would be limit of x squared as x approaches -1 from the left. That gives us 1. The limit from the right would be to take the second condition, right, where x is greater than -1. So this will give us limit of -1 minus 2x as x approaches -1 from the right. That also gives us 1. Thus, the limit as x approaches -1 from the left and the limit of the function as x approaches -1 from the right are both equal to 1. Therefore, the two-sided limit exists, and this is equal to 1, which is also the function value at x equal to -1. Therefore, we can conclude that the function is continuous at x equal to -1. So since the continuity is now settled, we can now use the theorem earlier to find the left and right derivatives using limits of the derivatives. Okay, so first, let's find the derivative of f of x. So if x is less than -1, the derivative of x squared is 2x. And if x is greater than -1, the derivative of 1 minus 2x is -2. So if we evaluate using the theorem earlier of the left derivative at -1, so this is equal to the limit of f prime of x as x approaches -1 from the left. So that would be the case where x is less than -1. So the limit of 2x will be -2. Also, the limit from the right, we can evaluate. So we get x greater than -1. So f of x is equal to -2. So the limit would then be -2. So in this case, the left derivative and the right derivative at -1 are both equal. Therefore, the derivative at x equal to -1 is also equal to -2. Therefore, the function is differentiable at x equal to minus 1. Okay, let's consider another function. We have here g of x defined as x squared plus x plus 2 when x is less than or equal to 1. And it's defined as 3x when x is greater than 1. Let's determine if this function g is differentiable at x equal to 1. So if you want to use the theorem earlier, again, we need to check for continuity first, okay? So we proceed with evaluating g of 1, right? So when x is equal to 1, g of x is equal to x squared plus x plus 2. And when x is 1, that should give us 4. Next, we look at the limit when x approaches 1 from the left. So this would be the case where x is less than 1. So we take x squared plus x plus 2. So the limit of this as x approaches 1 from the left is 4. Next, we look at the limit of g of x as x approaches 1 from the right. So this would be the case where x is greater than 1. So g of x will be equal to 3x. The limit of that would give us 3. In this case, however, the limit from the left is not equal to the limit from the right. Therefore, the limit of g of x as x approaches 1 does not exist. Therefore, the function g is discontinuous at x equal to 1. And because of this, we can right away conclude that g is not differentiable at x equal to 1. Now, what if we did not check for continuity first and right away proceeded with taking the limit of g prime? Okay, so note, if we take the derivative of g, so if x is less than 1, that would give us 2x plus 1. And if x is greater than 1, the derivative would be 3. Observe that if we take the limit of g prime of x as x approaches 1 from the left, so this would give us limit of 2x plus 1, which will give us 3. Moreover, if we take the limit of g prime of x as x approaches 1 from the right, so that would be the case where x is greater than 1, so the limit here would also be 3. So in this case, we get the left-hand limit and the right-hand limit both being equal to 3. So this suggests that the limit of g prime of x as x approaches 1 is 3. Now from here, you might be misled into thinking that actually g prime of 1 is 3. But since we already checked for continuity, we were able to show that g is actually not differentiable at x equal to 1. That means g prime of 1 actually does not exist. So if you're using the theorem we've shown earlier, be sure to check first for continuity before taking the limit of the derivative. Okay, that ends the second part of our lecture today. And if you want to watch this video again, feel free to do so. If you have questions, feel free to contact me as well. And when you're ready, I'll see you in the last part of our lecture today, where we'll discuss the chain rule. I hope you're excited. See you there.